Hello everyone. It's been a while since I've done a video. Reason being, it's taken me ages to perfect this, and I haven't finished it yet. I'm still working on it. What it is a little rotary table, a rotary table that rotates a laser. Got a small laser down here. This shines through a cylinder lens, and what this does, it creates a laser beam that shines a line. So what I'll do is I'll just put that laser beam in there so you can see what it does. So if I turn on the laser beam, when the laser, which is just a point laser, goes through this cylinder lens, it creates a line laser. So basically, if you look on top, it's still a straight line, it's still a point, a line, but in this direction the laser light has been spread out, and so what it does, it shines a line on whatever it touches. And then what this does is let's have a look. Laser beam. Rotation, there we go. Yeah, so what it does, it actually, this spins, and it spins around like this. It goes around and it's shining that light as it goes around. And so what we do is we place 3 beacons around this module, which is going to be mounted on a robot. So basically what this does is to find the position of a robot by shining this laser light on 3 beacons, which then ping a signal back to say when it has detected a beacon. What I'll do is this is all based on a friend's Instructable. I'll show you the Instructable because it will give you a better idea of what it is that we're doing. So yes, so I recommend taking a look at this Instructable. Just go to Instructables and just do a search for this robot triangulation using circumference. He's done a very good piece of maths which will calculate its position using triangulation using circumcircles. So basically we have 3 beacons and we have a robot in the middle, and it detects these 3 angles, and from those 3 angles and the known positions of these 3 beacons it can detect its position. So I recommend if you just pause my video and just go to this Instructable and watch his video and take a read of his Instructable. Basically he's shining the laser on one of these sensors, so it's just got a laser rotating around and it pings on one of these sensors, and there's 3 of these sensors. They're connected to an Arduino, which detects when they've been triggered. Basically what we're trying to do is to stop this from happening, so we know the position of the robot. Like I say, read his Instructable, and he's done some really fantastic maths here. It's brilliant the way it's done. It's worth giving that a good read if you're into this sort of thing, maths and trigonometry and so forth. But yes, so from the 3 angles, the position of the robot can be detected within these beacons. So it goes on to show you what it does. Now originally we were trying to get rid of all the wires connecting all the beacons to the microcontroller. So if we look like this, you can see all these different beacons are all wired together, and the object is to get rid of those wires basically, and to use one of these transmitters and a receiver to transmit the ping of the signal. At the moment he just has his laser. It's a passive laser just rotating, and it's just run on batteries. The batteries supply power to the laser, and batteries supply power to the motor that rotates the laser, and that's all that's needed. But I've gone a different way. So yeah, take a look at this Instructable, and then you'll have a better idea of where I'm going with mine as well. We're both trying to achieve the same objective, but we've gone slightly different ways, and so this video is about the way I've gone about things. So yes, my laser, my turret, shall I call it a turret, rotating table, it has a slip ring inside. Let's have a look. So inside there's actually a slip ring where I can feed wires in through to the rotating table, and I can actually fix a sensor to the table. So mine isn't really a passive turntable. I can actually connect things to another microcontroller that are mounted on this turntable. So that's why my turntable looks a bit more complex, is because I'm actually rotating things around some wires going through a slip ring, so I can connect things that are on this table basically. And this is what it is. I'm using an ESP8266 as my microcontroller, because what I can do is I can run a web server. One moment, yes, there we go. So I'm using this ESP8266 because it's got a web server on, and what I want to do is to be able to use a web page to display all the information that this is collecting basically. Now, as I was saying before, it's been a while, because what we've been doing is we have been trying to use these 433 megahertz radio transmitter and receivers. I've done a video about an issue that I had with these, where the pins were actually soldered to ground, and I've actually removed the crystal. If you do a search in my videos, you'll see a modification for this to fix an issue where if you test it, if you just test the output to ground, and if there's a short, the short is actually underneath this crystal, and you need to take the crystal off and replace it. But anyways, so what we're trying to do is we've got let's just move that there. So that there would have been tied with a sensor. So we'd have our sensor that picks up the laser coming from the when the laser hits it. Can I get that? So it shows a laser. Yeah. So when the laser hits that, what that would do then is would send a signal via the radio on this 433 megahertz radio, and there would be 3 of these. So as it spun round, it would trigger 3 of these, and these would be sending a signal back to our receiver. Now these are pretty basic receivers. I'll just bring a circuit diagram up, because what I what we were getting was, because there's such a large time delay between each pulse, that we were picking up a lot of noise, which then in turn triggered the microcontroller. So my microcontroller has an interrupt on one of the pins, so every time we received a signal on this receiver, it triggers the pin. But when we get noise, that also triggers the pin. So it was getting more triggers than what we wanted. Let me just bring up the circuit. Yeah, this is the circuit for that receiver, the 43 megahertz receiver. Basically, what we have our antenna, and we have a circuit for the resonance circuit to pick up the frequency being transmitted by the transmitter. This is amplified, and then it goes through demodulation through we have a matching frequency set up here, which then they merge together, so we detect the signal that we're actually transmitting. But then it goes through this filter, and the filter is pretty basic. It's just a capacitor and a resistor, and the values of these sort of only give you sort of like a pulse width of about I don't know, about 100 milliseconds or something, and then it just starts getting corrupt because of the capacity. Basically, it acts a bit like an RC circuit, but it's more of a filter than a thing, and then it gets amplified. Then after amplification, then this has got like an auto gain, so when it's quiet it sort of bumps it up. And what I've done is I've tried modifying the gain to give it a cap, but that didn't work. And then I also sort of reduced the pulse width of the signal, so it would only accept signals of a pulse width greater than sort of like 20 milliseconds. Anything less than 20 milliseconds it would ignore. And it sort of worked, but at that point we were having another issue. So I gave up with them because I was having headaches trying to overcome the noise from the signal, and eventually, in hindsight, basically what I found was that the majority of it was down to ambient light from the sun. I didn't notice, but when the light was shining through the window, these sensors, where are we? Yeah, these little sensors for the let's get some focus on that. Yeah, I've painted it black. Well, the transparent, actually. I don't know if I've got one. No, I haven't got one to hand. But they come transparent, and so basically, but the plastic is supposed to sort of filter the wavelengths you don't want. But I found that the sunlight that has every wavelength under the sun. Under the sun. Yeah, right. So anyway, that's why I painted them black, apart from the lens at the front. And so what was happening was when the sun shone and it reflected around the room, this was triggering from that. So if I'd have noticed that earlier, I would probably maybe still be going with these radio transmitters. But I've moved on from there. Like you do, you keep iterating and you go from one thing to another. So instead of using the 5.5, this is where I split from my friend who's done the Instructable. He went wiring them up, and is going back to using 433 modules. But I went a different way. I went infrared. So what I did was, I still had this sensor that picked up the laser sensor, but when it picked up, I put it through a 5.5 timer, and this created 38 kilohertz pulse, a carrier, which I then transmitted on an infrared LED. So what I could do was, instead of using radio waves, I'm using infrared to send the signal back. So I had this, let's just call it a switch, light switch. So when the laser hits it, it switches on, which then turns on the 5.5 timer, which creates 38 kilohertz pulse width modulation. Basically, it's a carrier for the infrared, so then this will then transmit at 38 kilohertz. And because it's transmitting at 38 kilohertz, I can use one of these receivers, which is a standard NEC receiver, which has a filter to filter out other light sources apart from infrared, and it has a demodulator inside to demodulate the 38 kilohertz to a single pulse. So basically, I'd changed from the radio setup to infrared setup, and this was working quite well. But of course, I hadn't realised that this was the issue with ambient light. Anyway, so I was still getting exactly the same interference. So then what I did, I went a different way again. So instead of this picking up the signal and sending it through this 5.5 timer to create a carrier wave for the infrared LED to be picked up by this. So what basically I'd have three setups of this and just one of that. It just hit me that I can put this 5.5 timer and pulse the actual laser. So the laser is being pulsed at let me just get a focus in there. Yeah, so I was pulsing the laser through this at 38 kilohertz. So because the laser light is modulated at 33, I did not need to put it. I did not need to put this modulator on the beacon end, because what happens is the laser was then modulated through this. So my laser is actually, when it shines, it's actually shining a 38 kilohertz modulated light beam. And so when it hits this switch, it actually switches this switch at 38 kilohertz, which in turn lights the LED at 38 kilohertz, which then came back to my infrared sensor at 38 kilohertz. So all the light had been converted to modulated 38 kilohertz, which then reduced the noise that this was creating, because when I got noise from this, the noise wasn't actually 38 kilohertz, only my pulse from my laser was 38 kilohertz. So basically this then filtered out the noise from this. But the issue I had was the range. Well, not so much the range. There was still a bit of noise from ambient light, so I thought I'd go a different way. Then I thought, well, why not just send the laser back? And so that's what I've done. I've come up with now Now I'm just sending this laser back with a mirror. So if I've got a mirror here, well actually let's start with just a normal mirror, and what we have to do is we have to get the laser light from this back to the sensor on here. So I've mounted the sensor and the laser on my turret, and they both rotate at the same together, and then when they hit a mirror, if I put a mirror here, this if I put that, let's get it in shot, if I put that there, and my laser light will come, let's just get that sort of right, there we go. So my laser light comes out of here, hits my mirror, and then is get reflected back. But the next step is to get the light, when this this laser rotates, you can see that the light is reflected back in exactly, let's see if I can get that down there. Is that showing up? So I've got my laser light coming. I'll just turn the light off for this bit, then it'll show up a bit better. Let's see if I can just get a bit not so dark. Alright, try and get it to focus on something. Nope. Right, that's better. Right, we'll leave it at that. So yeah, so as my as this rotates, my laser light is rotating round, and you can see that it's going into the mirror. And then if the laser is not lined up perfectly, let's just move that round a touch. There. So you can see that the light comes in, hits the mirror, and then gets reflected off. But as the turret rotates and it becomes aligned with the mirror perfectly at perpendicular, you can see that the light is being shone and comes straight back. So then we can actually, this sensor will then activate knowing that I'm in the exact position. So as it comes across, you can see the laser light going, it hits and activates and then deactivates as it continues. I can hope you can see that. But we have an issue with this. Because the robot is going to be moving around, it can be in different positions to the mirror. So I'll just move the mirror to show what happens. If the mirror moves, if the robot moves, you can see that the reflection changes as the robot moves, and so basically the only time that it's correct is when it's actually perpendicular. So at 90 degrees to the light is the only time it's correct. If the robot is sort of in that direction to the mirror, this is not going to work, because it's not going to hit the mirror and line up. So there's a special mirror that we can use. So to show this, I am going to go 2D first. So can you see this? This is a mirror. This is two mirrors, and what I've done is held them together. Let's turn my light back on now. Ooh, sorry about that, guys. I've just blinded everyone. There we go. So we've got this mirror, and I've held it together. Two mirrors held it together at 90 degrees to each other. So this is this is how cat's eyes work. You know the cat's eyes in the road? When you shine a light, when you're driving down the road and your headlights shine on a cat's eye, the light is reflected directly back towards the source of the light where it's coming from. And this is how a cat's eyes work. Well, you can either have a round one or you can have two flat ones. And so I want to try and demonstrate this and show you how it works using my laser. I will just turn the light off again and try and get some a decent colour temperature. I think that's more like it. There we go. Nope, shouldn't have clicked. Try and get on this. Tell you what, I'll just try and get onto this board. Has that got it? Yeah, it looks a bit crap, that, doesn't it? Anyway, you can see the laser quite well. So obviously this mirror, if I hold it like that, say it's horizontal, we can have it in that direction or we can have it in that direction. Well, if we have it in this direction here for the laser to come, I should be able to show it because right, I don't know if you can see that, but as it doesn't matter where can you see me turning the mirrors? So depending on where I have the mirrors like this, it should not make any difference whatever. What should happen is the light should hit it. When it hits it, it should come back directly in the same direction it came from. So if I move there, ignore that one over there, but right, there we go, I've got it now. Can you see that line? Can you see that line there? As the laser, there's one parallel to the one that's going out and the one that's coming back. I think I need to lift it up. The trouble with this, it comes back in exactly the same direction it's coming from. So I have to get the card in the right sort of angle for it to show up. But you can see it's actually parallel. It doesn't matter if I turn the mirrors slightly, it's still parallel and comes in back exactly as it comes. If I turn the mirror this way, oh, hang on, it's shining the wrong light. Ignore that light. That's just the bigger mirror. But it's just the one parallel that I'm trying to show that is reflected back. Okay? So that is okay in two directions, but what if the laser is out in the horizontal plane? Well, what we really want is this, and add a third mirror. Let me turn the light back on again. The trouble is with the third mirror, I cannot show you it reflecting on a piece of card, because what effectively happens, so can you see that I've just added another mirror on the end there, which is at 90 degrees to the other two mirrors, and what this does is it creates a corner prism reflector, and so any light going into that corner, no matter whether it's coming from up, down, left or right, it's always going to go back in the same direction that it came from. Yeah, I don't know if you can see there, but well, it'll show you better. So that was my prototype to actually show what was happening. Once I've got that made, I have actually made some beacons, and these are my beacons. And these are my mirrors. Now I am going to put this underneath the camera. Right. Now I don't know if you can see there, but let's see if I can I don't know if I can focus on it because it's the camera lens I want to show you. Let's try. I wonder if it'd be better without the right. I don't know if you can see there, but in the middle of that is my camera lens. It's right in the middle, because basically any light, let's see, any, there, well, you can see a few images of it, but I don't know if maybe I should put a ring around the camera lens. Right, you can sort of see it there in the middle. It's the whitish bit is actually my lens. Now if I tilt this, the lens, the camera is always going to be in the middle, because the light shining to the lens, or the reflection of the camera, will always stay in the direction that the light comes from. So basically, this, what I'm trying to show is that this lens can be at any angle to the laser that's going to come out and through here. So if I put this, the thing is, because the laser is coming out and hitting the lens, it's always going to be exactly in the same direction it came from, and it's only going to be that amount of lens. So can you see, even if I have it at, is that sure? Let me turn the light off again. So right, I'll just, actually that's not showing up so well. I think what I need to do is give me a minute. I'm just going to try and set this up because it's okay. I don't know how well that shows it, but tell you what, let me get my ruler. Right, you see my ruler here? That is at this angle. That is the angle at which I have got the prism set. There we go. It's a bit hard to see, but you can see what we're looking at is this little tiny bit of light being reflected back from, this is the main outgoing light, and then we've got the little bit we've got the little bit of light coming back, because it's only the width of the actual prism that's actually coming back, it's not the big beam. And so as the laser passes, you can see that it only lines up when it's in direct line with the actual beacon. But let's say the robot moves, so we'll emulate this by rotating the beacon so it's actually pointing in another direction. So if I rotate the beacon like so, you would expect the light to go off in another direction, but it doesn't. It still comes back in the same direction it's coming from. So if I rotate this turret here, you can see that the light is still being reflected back exactly where it came from, even though the angle of the beacon has changed. It went from that angle to that angle, but it still reflects it in exactly the same direction the light has been shone into it. Well, I hope so. Hope that made some sort of sense. Just give me a minute. Right, okay, let's see if I can show it a bit better on my CAD. Well, hopefully I can show it better here. And yes. So what the setup I've got at the moment. So I've got my rotating table. and I've got my laser coming out, giving this line of laser light. And then what we can do is I can put my beacon in front of this laser light. So if we look on the top, we have our laser. Let's just go like this. So as my laser's turning, it will actually hit the let's call it a prism for the sake of it. It's 3 mirrors, but you can actually let me just show you one moment. Yes, these are what they are. What you can actually do is you can buy these. The thing is, they're a bit on the pricey side. Oh, you can see it better. Oh, you see it better there. Basically, you see these. This is a prism where you've got like 3 sides that have been ground away to form the internals. Let's see. Yeah. So that, if you can imagine, this is a prism. But I need 3, so you're talking 33 quid there for these. But I actually had some mirrors, and they're actually special mirrors. Let me just see if I can. They're called first surface mirrors because the actual surface is on the front and not the back like normal mirrors. The actual surface of the mirrors are on the front. I got these out of some old flatbed scanners back in the days when it was all scuzzy and stuff. I'm talking really old flatbed scanners, not today where we've got LEDs. This is before the days of LEDs. I got these out of some old scanners when it used to be the cathode, the fluorescent tube and mirrors reflecting. Anyways, so I've actually made these up myself because I had them. But as I say, you can actually buy them, and these are what they look like, sort of thing. But like I say, the price is stupid. I would have thought they'd be a lot cheaper by now. Anyways, so let's continue. I sort of went on a. Well, actually, I just wanted to show you what they are, and that you can actually buy them instead of having to make them. So if we look on top, as the laser comes in, the light is going to be shone exactly the same direction it comes in. So if I put on the reflection, where are we? I've put this somewhere. That's my rotation, that's my beacon. Oh, laser reflection, there we go. So yes, so if we take this, where are we? There we go. Right. So as it hits the mirror, when it hits the mirror, there. Oh, hang on. Can I make that not 0.1? When it hits the mirror, there. Let's make that 1. It's the mirror there. It's going to reflect exactly back the way it came. So it's going to come back right into this sensor. Yeah. So as soon as it hits the mirror, it's going to reflect around and come back exactly in the same direction. Well, actually, it's not. It's going. Sorry, I've got that wrong. Right. When it hits the mirror, it's going to be coming back in the same direction it's coming from. But when it hits it, it'll be there to start with. Right. So if you imagine my sensor is in the same place as the way I'm sending it out. That sends the light outwards. It reflects off this mirror here, or it could be this top mirror, and it goes down to the bottom mirror, but basically it goes in and then comes across to this mirror, and it comes back in exactly the same direction it's coming from, but it's slightly offset because it's on this side of the mirror. But as this rotates, let's just go okay with that. As this rotates here, let's just try and get that rotation. There we go. As that rotates towards the center, so if we go like that, and now it's on the center, you can see, where's my laser reflection? You can see that it's reflecting on this mirror right at the point, so this is actually going to come back from this point, and it's going to be in the right direction, and it's actually going to hit the sensor as it rotates. And then as this, cancel that one, as that rotation continues, where are we? It continues round, this actual rotation follows it. I should have actually put that on the end of there, really, shouldn't I? I wonder. Yeah, so this this actually there we go. So as this moves across, this will be then reflected. Oh, sorry, this one will then be reflected across to this side of the mirror, and this will end up over there going at that angle, because it's coming back in the same direction. But because it's not in the center of the actual mirror, it is actually getting reflected here and there and coming back. But when it comes back, it actually misses the sensor. So it's only when it's truly lined up that the actual signal comes back true and hits the center in the middle. And to ensure that this happens, let's just get all my drawings back to normal. There we go. And get that rotation back to normal. There. To ensure this happens, what I have done, when it's exactly in the middle there, so it's actually getting it right into that corner point right there, so it's in this area, so there's no offset. If it was hitting over there, there'd be this big offset, but at that point there's no offset, so it's coming back exactly where it came from. And to make sure I have no ambient light, I've stuck my sensor inside this box. That's the wrong thing. There. I've stuck my sensor inside this box, which is sealed from ambient light, and the laser has to come down this tube to hit the actual laser. So any ambient light coming in from any other direction should not be affecting this laser. So let's just get everything back to normal. I don't like to leave my drawings a mess, so if you don't mind, I'll just sort that out. Yes, so I hope that made it a little bit clearer how it knows when it's precisely in line with the beacon. But of course, if we look on plan, this will still happen even if, let's just get my beacon and let's just transform. Even if this beacon is slightly out of alignment like this or like that, it will still reflect it back in the same direction it came, but obviously still with the offset as well, because it's going from one mirror to the other, what happens is, because the mirrors are on a slight angle, the refraction on this mirror that is different gets the reverse done to it on this mirror, because it's going in the direction, so the two refractions total up to the same refraction as if it was straight on, like that, basically. So you get an increase in angle on one side, a decrease on the other, or if you're going the other way, you'd get a decrease in angle on that side and an increase in angle on this side. But they both total up to the same angle, which is 180 degrees backwards. One moment. Right, I just want to point out one thing. On my rotating table, as it rotates, let's just go there again. As that rotates, what I have is a little hole here on this disc, and I have a sensor here that's when it rotates round, that hole lines up with that sensor and it pings a signal. So I've actually got two signals coming from this. I've got the signal when this has done a full rotation, and I've got a signal when it hits a beacon. And what I've done is I've put both these on my oscilloscope. Let's just bring that back. So I've got my my little prism thing there, so you should always see the camera lens inside that when I rotate it, because the light comes in the direction it's coming from. And if I put that in front of the beacon, it can be on piss like that, it doesn't really matter, as long as majority of it is pointing towards the beacon. I will start this spinning, and what it is I've got the yellow trace which is going to the sensor on the disc for one full rotation, and then the other blue one, or cyan or whatever, is when this beacon actually hits and gets reflected, when the beacon reflects the light back. And what I'll do is I will actually move this around like this to show you that it doesn't alter the signal coming back. Let's start it up. So there we go. The yellow trace is it. Hang on, let's just right. The yellow trace is when it's pointing in this direction. When it's pointing towards my finger, that's the yellow trace. And when it's pointing to the beacon, well, I'm calling it a beacon, but it's the crystal. It's actually the it's the mirror. So what I can do is let's just go zoom in. Channel 4, channel 2. Very well. There we go, normal. Right, so yeah. Right, so you can see that my mirror, if I move it in one direction like this, if I move it closer to this point, we get closer to the I'll call it the datum on the yellow, and if I move it round, you can see that it moves further away, like that. Okay, because it's taking longer from the pulse from the mirror to get to where the datum is. So what I'll do is I'll just leave it here. Tell you what, let's put it sort of in between there. Can I zoom in a bit more? It's a bit better. Right, so I'll just move it out a bit. Right, so what I just want to show you is that the point is where this pulse is when the laser light hits right on the center point of that prism. And so if we rotate it around that center point, this should not change. I mean, it's bouncing around at the moment. This is one thing I've got to get rid of. I've got rubber bands as belts here, and I'm getting a bit of backlash, and that's why it keeps bouncing backwards and forwards and doesn't stay a steady signal. But what I need to do is just show you that this turning on the spot does not actually alter the position. It does double it up a bit. I'll have to look into that. But you have to remember, these are made by me, these crystals, and I'm not to the nanometer of wavelength of light. But you can see that I am turning it, and it's not actually altering its position. But if we move round, this does alter the position. But basically, we're always getting the light shone in the direction it comes, even if we twist these mirrors. It doesn't do the thing that a normal mirror does. If we put a normal mirror in front, yeah, that right. Okay, that's supposed to have happened. Right, yeah. So it's only if I rotate a normal mirror, you can see it has to be facing the actual laser. Oh, I got this. Well, I can't. I tell you, it's that hard. I can't even line it up myself by hand. I'll be lucky to get a spot, I think. But obviously, the other mirror, that doesn't matter if it's rotated. Okay, so yeah, that's what I wanted to show. And so I'm still working on this project to I'll tell you what I haven't done. I haven't set up. No, there's still a bit more. Yeah, I nearly forgot. Right, I'll set up two more of these. Two more of these beacons or reflectors. Just give me one moment. Yeah, okay. So you can now see 3 pulses. I've got another beacon. Right, so there's one beacon, which is this beacon is just before the is this one here, just before the datum, and then as it goes past the datum, there's another one there, which is a bit out of shot up in this direction, and the other one is still out of shot in this direction here. But you can see the 3 pulses. You see the 3 pulses in between each revolution. There's 3 beacons being pulsed there. So from them 3 beacons, so we can measure the time between each pulse as it rotates. And what we do with those times is we send them to an application. And the application I have is a web page on this ESP8266. There's actually a web server, and it has a web page on it, and we can have a look at the web page on this microcontroller. One moment, I'll get it. Right, here it is. This is the web page. I just typed in this to get to the web page. So basically, my browser on my PC is actually connecting to the ESP through Wi-Fi, Well, actually, the Wi-Fi on here is connecting to my local network, and on my local network I'm connecting to the ESP8266. You can do it either way. You can go direct if you want, but that's the way I've done it. Anyways, so what I've got is I've got this web page which I'm looking at on, well, ESP8266 has sent me this web page, and what this web page does is every second it asks for the times that we see here. So every time it starts at this pulse, then it asks for the time between there and there. Let's make that bigger. Right, so there we go. So we have this. This is at my datum pulse, which is every time this pulses, it does one revolution. And then what we do is we look at the time between the start of the revolution and the first beacon, and then we look at the time between the first beacon and the second beacon, then the time between the second beacon and the third beacon, and then the time from the third beacon to the completion of one revolution. And we just keep repeating that, so all these should be exactly the same because nothing is moving basically. So this is what my web page is asking for. It's asking for these times as it pulses. Well, oh, I wonder what the hell that disappeared then. Right, so yeah, let's get rid of that. So yes, and we can see them times coming up here. So this is just a bit of code to tell me that it's actually spinning. What I've done is if you look at my little picture of my rotating thing, I did a picture, and you can see that it's rotating. And if I turn this off, there we go. It says it's off, and my little picture stops as well. So that was just a little thing I wanted to do on my web page, just to practice and see if I could do it, sort of thing. So I've got my thing. If I turn this back on again, there we go. It says it's on, and my little picture shows the little wheels. So you've got that spinning, and you've got even that little wheel spinning. So I thought that was pretty cool. Anyways, so there are the times. We could measure these times, but what happens is this web page asks for asks my one moment. This web page asks the ESP8266 what these times are, because every time it pings, it does an interrupt on one of these pins, and it records the time between each one. And that's what we have here. So here we have our total angle, which is all these angles added up. I have a check angle, which is a complete full rotation. That's how long it takes to do a full rotation. And these so from 0 to 3, 0, 1, 2 and 3, those all should add up to this, and if they don't, we've got an issue. And as I said earlier, I have this, I've got a rubber band here and a rubber band here, and what happens is as this rotates on my bearings, it gets a bit stiff and slack. I just knocked it up, you know. It's not precision built, this thing. So I am going to change the way this connects. I'm going to put a timing belt connection between the motor and the spinning thing, so that I don't get this bouncing of the rubber bands. They sort of the rubber bands get tight and slack, and it upsets the timing, and it doesn't always give the correct. These three don't add up to that fourth one, so I need to sort that still, so I'm still working on it. But Yes. When it doesn't bounce around, I've made it so this shows green, and it gives me the angles. Let me just show you what's happening. So what I can do is, if we get that up, so these let's have a look. Yeah, on that one, let's have red. So this value here is this value. So this value is that time converted to angles, and then I've got this. Let's have a look. I've got this value, which is converted to angles, and I have this value here, which is this one converted to angle, and then we have this value, which is this angle here. And so this angle, this right, so this angle, and these two angles, well, actually these two angles should add up to this angle, so that gives me the angle between these two beacons there. This angle is between these two beacons, and this angle is the angle between these two beacons. But all these angles here should add up to this one. So all them angles should add up to this one here. So if I add all them three together, it gives me this total here, and so that total and this total should be the same. And if they're not, then I just don't use them. When they are the same, then I use them, and this goes green. So this then gives me the angles I am looking for, which, if you've watched my friend's Instructable, is how we define the position of the robot using those angles in between those beacons. So I hope that how do I get out of that? There. So yes. So that is. I've gone for the web page. My friend has gone for the processing software. But either case, all the hard work should be done on the actual PC that's actually viewing the thing. So I hope the long delay and me ranting, trying to explain what I've been doing. Let's see if I can get that web page down here. Yeah. So yeah, so basically this is what I've been doing, and for the last month, trying to get this right, and I've still got a bit of work to do. Like I say, I need to redesign my rotating platform. I'm going to change this motor. What I'm going to use is instead is the same as what my friends used, and that's one of these motors instead. Let's just zoom in on that. No, that were rubbish. I'm making a really bad job of that. Yeah, so these are, I think these are great motors. You can get them at different voltages, different speeds, yeah, which is great. So let's just bring everything else back. So we've got a nice picture. There's my web page. Yeah, that looks cool, doesn't it? Yes. So what I'm doing is very similar to my friend's Instructable, but we've gone sort of slightly different ways to it. I hope some of this made sense to you. I hope some of you liked it, but I just thought I'd have to do a video. Sorry it's so long, because it's been quite a while since I've made a video. Yeah. There's nothing more to say. I don't think I've forgotten anything else. I'll tell you what. I'll just pause it. No, I couldn't think of anything else. I've just changed the view of the. Oh, it looks horrible. That. Yeah, so you can see how it's running in real time. Nah, that's it. I think. Right. Catch you later, guys. And if you made it this far, thanks for watching.